Alien civilizations can create detectable accelerators of black hole particles. July 28, 2019. The nightmare of particle physics is the dream of astronomers looking for extraterrestrials, says astrophysicist Brian Lackey of the Princeton Institute for Advanced Studies in New Jersey, who proposes that advanced civilizations can build a black hole particle accelerator. Alien civilizations can create detectable accelerators of black hole particles to study physics. Astrophysicist Paul Davies of Arizona State University told Hamish Johnston of Physics World that he believes it is very difficult for planet Earth Homo sapiens to understand why an advanced civilization would build a particle accelerator to study physics and energies of the like scale. Davies conjecture, why would they do that? Perhaps to create a children's universe or some other exotic sculpture of space-time. Why do that? Perhaps because this hypothetical civilization feels that it faces a threat of cosmic dimensions. What could this threat be? I have no idea. However, a civilization that knows a million times more than humanity can perceive all kinds of threats of which we are unaware. Lackey's study, ETI at Planck Energy, when particular physicists become cosmic engineers, asks what the Fermi paradox means. Are we alone or is star travel rare? Can general relativity be coupled with quantum mechanics? Searches for answers to these questions can cross, Lackey writes. An accelerator capable of energizing particles on the Planck scale is known to require cosmic proportions. The energy required to operate a Planck accelerator is also cosmic, on the order of 100 m Sol C2 for a hadron collider, because the natural cross-section of Planck physics is so small. If the aliens are interested in fundamental physics, they could resort to cosmic engineering for their experiments. These colliders, Lackey says, are detectable through the sheer amount of pollution they produce, motivating a UV study program. I investigate what types of radiation they would emit in a fireball scenario and the feasibility of detecting UV radiation on Earth, particularly UV neutrinos. Although current UV neutrino limits are weak, Kardashev-3 UV neutrino sources appear to be at least 30 to 100 mpc on average if long-lived and isotropically emitting. Lackey contemplates the feasibility of much larger UV neutrino detectors, including an acoustic detection experiment that spans all oceans on Earth and instruments the entire Kuiper belt. Any detection of UV neutrinos implies an extraordinary phenomenon at work, whether artificial or natural. He notes that the universe is very weak in all types of non-thermal radiation, indicating that cosmic engineering is extremely rare. Lackey suggests that if electric fields are used for acceleration, the particle accelerator would have to be at least 10 times the radius of the Sun. However, a magnetic synchrotron accelerator could be slightly smaller. Lackey adds that normal materials would not withstand strong electromagnetic fields. But a natural solution already exists in the cosmos. One of the few places where this high energy density could exist is near a black hole, which he argues could be harnessed to create a Planck-scale accelerator. And if such a cosmic collider exists in a corner of the universe, could we detect it here on Earth? Yes, says Lackey, who has completed calculations that suggest that if such an accelerator exists, it would produce electron-volt yada neutrinos eV or 1024eV that could be detected here on Earth. As a result, Johnston reports, Lackey is calling astronomers involved in the search for extraterrestrial intelligence SETI to search for these ultra-high energy particles. This is supported by Arizona State University astrophysicist Paul Davies, who believes the search should be expanded beyond traditional telescope research. Johnston writes, like humanity, it seems reasonable to suppose that an advanced alien civilization would have a keen interest in physics and build particle accelerators that would reach ever higher energies. This energy escalation could be the result of the nightmare scenario of particle physics, in which there are no new energies and energies between standard model TeV energies and 1028 eV Planck 10x eV energy, where the quantum effects of gravity become strong. However, quantum physics suggests that the density of electromagnetic energy required to reach Planck scale is so large that the device would be in danger of collapsing into a black hole. However, Lackey points out that an intelligent designer could in principle circumvent this problem and achieve Planck's energy is technically permissible even though it is extremely difficult. However, the particle collision in dozens of XeVs is only half the battle. Lackey estimates that the vast majority of collisions in a cosmic collider would be of no interest to alien researchers. For useful information on Planck-scale physics, he concludes that the total accelerator collision rate would have to be about 1024 times that of the Large Hadron Collider. He explains, as such, Accelerators built to detect Planck events are extremely useless and produce large amounts of pollution. While much of this pollution is from extremely energetic particles that could in principle reach the Earth, it is unclear whether they could escape the intense electromagnetic fields within the collider. Also, like colliders here on Earth, the builders of a cosmic machine would probably try to protect the surrounding region from harmful radiation. Lackey's analysis suggests that neutrinos are the only particles likely to hit Earth.